Yo, what is up, guys? Have you seen the prices of memory and storage lately? They are absolutely blasting into orbit. Building a proper home NAS right now feels like you need to sell a kidney, but don't panic. Today, we are hacking the system. We're taking our favourite little powerhouse, the Raspberry Pi, and turning it into an absolute beast of an enterprise-level file server. And the best part? We're going to do it by hooking up to our Raspberry Pi those dirt cheap, dusty drives you've probably had shoved in a desk drawer since Bill Gates said 640 kilobytes ought to be enough for anybody. Yeah, those drives. We are going to unlock insane data center level speeds. I'm talking about feeding this Raspberry Pi an unimaginable amount of disk traffic just to watch it absolutely chew through it without breaking a sweat on your home network. You think a budget DIY Raspberry Pi home NAS has to be slow? Oh buddy, you are not ready for the mind-blowing speed multiplier we're about to pull off. Grab your energy drink, hit that like button, and let's build the ultimate Raspberry Pi home NAS. Alright, let's check out the loot drop for this build. To craft this rocket ship home NAS, I'm rocking a Raspberry Pi 5 with 4 gigs of RAM. But hey, don't sweat it if you don't have this exact Raspberry Pi model. You can totally use other boards or even different architectures as long as they can hook up to an NVMe drive. That is the secret sauce. To house our Raspberry Pi, I'm using the absolutely beautiful Pyronman 5 case. It's got beefy cooling, a built-in status display, and most importantly, an NVMe expansion board. I actually did a deep dive review on this exact case. Link is in the description, but do not click it yet. Watch this video to the end first, trust me, you don't want to miss what's coming. And for storage, we are going full budget hacker mode. I've got an ancient mechanical hard drive slapped into a cheapo AliExpress USB enclosure. I also have an NVMe to USB adapter here, but that's totally optional. I'm just using it to hook up the NVMe to my PC real quick to nuke all the old data off it. See this black PCB on the desk? That's the Pyronman expansion module. Now, I bought literally the smallest, cheapest NVMe drive I could find. And because we're building a proper home NAS and not some janky science fair project, I 3D printed a custom enclosure for the hard drive and a sleek little stand for the Raspberry Pi. Aesthetics matter, guys? Alright, hardware time. We drop the expansion board into the case, plug in those delicate little ribbon cables and snap the chassis shut. Boom! Our professional grade Raspberry Pi home NAS is physically assembled. Hit that power button and let's fly. Wow, hold up guys. Before we hit the desktop, you might get hit with a nasty little surprise. The boot order is hard-coded into the Raspberry Pi EEPROM, and it might try to boot off those blank external drives we just plugged in. Don't panic. You can just wait a minute for it to time out and hit the SD card, or use the official imager tool to force the boot order. Alright, we are in. Welcome to your first step into the world of supercomputers. To make building this Raspberry Pi Home NAS ridiculously easy, I wrote a custom runbook. It's got every single command we need, and it is pure copy-paste magic. I'll drop it in the pinned comment below so you can follow along. First up, let's permanently fix that boot order. We pop open the terminal and run sudo rpi-eprom-config-edit. We need to force our Raspberry Pi to only look at the SD card, so we change the boot_order value to exactly 0x1. Save it. If yours was set to something else, give it a quick reboot. Mine is already dialed in, so we keep pushing. Next, we hit the standard update and upgrade commands. We want a rock-solid Raspberry Pi Home NAS, which means no weird software surprises later. While that's cooking, let's install a legendary utility called Glances. This is exactly how I'm going to prove to you that this tiny Raspberry Pi absolutely destroys professional NAS gear. Let's fire it up! Look at this dashboard. It shows everything, but keep your eyes glued to disk I/O, I/O weight, and network traffic. That's where the magic is going to happen. Finally, we need to install the Pyronman software to fire up the RGB, the cooling fans, and that sick OLED display. If you're rocking a naked Raspberry Pi board or a different case, just skip this step. Let's do a quick reboot to activate the case controller. And boom! We are back. Look at that OLED display shining. We've got live CPU, disk and temperature stats right on the front of our home NAS. Alright, the base system is purring like a kitten. Now it is time to actually build our Raspberry Pi Home NAS. First things first, let's slap Samba onto this bad boy with standard install commands. But before we hook up any physical drives, we need to know the absolute maximum limit of our Raspberry Pi and our network. How do we do that without disk bottlenecks? We hack the matrix and build a temporary RAM disk. We're creating a directory at /mnt/memdisk and allocating 2 GB of pure ultra-fast memory to it. But hey, warning, listen to me. Be careful here. Make sure you have enough RAM and that swap is enabled. If you're running a headless server OS, leave yourself at least 800 megabytes to breathe. I'm running the full desktop version on my 4 GB Raspberry Pi board, so I'm splitting it down the middle, 2 GB for the OS, 2 GB for my blazing fast mem disk. We slap the right permissions on that folder, and now it's time to edit the Samba config. Over in my runbook, I've got a base config ready to go. Just copy-paste it right to the bottom of your file. You can tweak the permissions later, but for now, we save it and restart the Samba service. Let's make a quick test folder just to prove we're alive. I pop open Windows File Explorer, type in the IP, and boom, there is our test folder. We are officially on the network. Now let's generate some heavy traffic. I've got this slick little script that grabs empty data from /dev/0 and dumps it into our mem disk. We are telling it to write 19 files, 100 blocks each, exactly 1 megabyte per block. That is 1.9 gigabytes of dummy data instantly teleported into our RAM. Run the script. Wait a couple of seconds. And done. We check the disk space and yep, 1.9 gigs locked and loaded. It is benchmark time, baby. Over on my PC, I drag those files from our new Raspberry Pi Home NAS straight to my desktop. Are you seeing this? 110 megabytes per second. We are completely maxing out a gigabit connection. The network is at 100% utilization and the Pi doesn't even care. This proves our Raspberry Pi hardware, OS and Samba setup have absolutely zero bottlenecks. It is perfect. Alright, the RAM disk was a fun little flex, but let's get back to reality. It's time to see what this clunky mechanical USB drive can actually do on a budget home NAS. First, we nuke the mem disk, free up our RAM, and shift our focus to the hard drive. Step 1, we wipe everything off of it. Next, we create a fresh partition. To keep this video moving fast, I'm using a one-liner parted command, but if you want to geek out and do it manually, you can totally use fdisk or a GUI like gparted. Next up, we format it to ext4, the absolute standard for Linux. We aren't doing any fancy tuning here because, spoiler alert, you are about to see a tragedy unfold anyway. We mount the new file system to /mnt/USB disk, update our Raspberry Pi Samba config one more time, and restart the service. I'll make a quick test file, pop open File Explorer, and yep, the drive is mounted and shared over the network. Now let's get to the magic, the stress test. Look, just copying massive movie files is useless for benchmarking. Even ancient spinning Rust drives can handle sequential reading and writing pretty well. To find the actual limits of this drive, we are using Microsoft's Disk SPD. This is a legendary powerhouse console utility designed to simulate a real-world multi-user nightmare. Think multiple people editing docs, saving, deleting and moving tiny files all at the same time. Link for that is in the comments. Here is our battle plan for the command line. -C2G creates a 2 GB test file. -R forces pure random access. -W25 means 25% writes and 75% reads. -B 4K sets the block size to tiny 4 kilobyte chunks, the ultimate HDD killer. And finally, -SH disables all Windows caching so we get the raw, brutal truth over the network. While Disk SPD is running on my PC, let's look at the Raspberry Pi using that Glances dashboard we installed earlier. Oh man, look at the I/O weight and disk I/O columns. This is absolute carnage. The I/O weight is hitting 75%. That means our Raspberry Pi's CPU is literally just sitting there, twiddling its thumbs, waiting for the mechanical drive to violently thrash its red and write heads around looking for sectors. Meanwhile, our actual data transfer is limping along at maybe a couple of megabytes per second, system doing nothing, disk screaming in pain, and the test is done. Let's look at the Disk SPD results. Total average speed, 0.33 megabytes per second. Read speed, 0.44 megabytes per second. Write speed. Are you ready for this? 80 kilobytes per second, guys. That is straight up 1990s floppy disk territory. Mechanical drives absolutely choke and die on random I/O. But do not rage quit your Raspberry Pi Home NAS build yet. Now it is time for the magic trick. We are going to tag in our NVMe drive, build a hybrid array, and absolutely obliterate these numbers. Let's go. Hold up, hold up. Before we actually build this Raspberry Pi Home NAS, I need to pause the game and explain the absolute cheat code we are about to activate. We are going to use a technology that until recently was locked away behind insane paywalls in high-end, stupidly expensive enterprise disk arrays. It's called storage tiering. Here is how the big boys in the data centers do it. The storage controller has super fast NVMe drives, or even battery-backed RAM, sitting right at the front. That is Tier 1. When you save a file, the controller writes it to that ultra-fast Tier 1 cache and instantly tells your computer, done, saved. But obviously, building massive petabyte arrays out of pure NVMe or RAM will bankrupt you. So to solve that, the controller is hooked up to a massive army of cheap, slow mechanical hard drives. That is Tier 2. The controller constantly watches Tier 1. When it starts getting full, it takes all that saved data and flushes it down to the Tier 2 mechanical drives in massive sequential blocks. And remember what we said earlier? Mechanical drives love sequential writes. So the background write speed becomes absolutely cosmic. Because of this, write confirmations are instant. And if you go to read a file you just saved, lightning fast because it's still sitting in that Tier 1 cache. You only ever deal with the slow mechanical speeds if you pull up some cold ancient data you haven't touched in months. And guess what? This God tier technology is now available for our DIY Raspberry Pi Home NAS. It's baked right into Linux through a module called Bcache. Bcache lets us glue together superfast NVMe drives as our Tier 1 cache and bolt them onto literally any cheap, slow disks for our Tier 2 massive storage. It even aggressively uses your Raspberry Pi's free system RAM to cache the absolute hottest data. So here is the master plan. I am taking this dirt cheap 128GB NVMe drive for my cache and pairing it with my dusty old 1TB mechanical drive, which means our home NAS is getting a full terabyte of network storage, but with NVMe level access speeds, practically for free. Are you hyped yet? Let's build this monster. First things first, we shut down Samba and unmount that turtle speed USB drive. Get it out of here. Next, we pull down the Bcache tools package using our standard apt install command. And guys, this is beautiful. There is no downloading source code, no compiling for 3 hours. It is already pre-packaged and ready to deploy. Now, we wipe the slate clean, we run a quick wipe FS on our mechanical drive, and another one on our fresh NVMe. Once they are totally blank, we cast the ultimate magic spell, make-B cache. We tag the NVMe as our ultra-fast caching device and the clunky USB drive as our massive back-end storage. Technically, the drive is alive right now, but we don't settle for stock settings on this channel. We are going to overclock this cache so it holds more data and writes to the mechanical drive way less often. But quick PSA, listen to me closely. Doing this adds a tiny bit of risk. If your NVMe drive randomly dies before it flushes the data to the hard drive, that data is gone. Poof. If absolute data safety is your priority, you should grab a dual NVMe expansion board for your Raspberry Pi, set up a mirrored RAID, and use that as your cache. But today, we are living dangerously for maximum speed. Let's inject 4 custom parameters straight into the kernel. Number 1, we force write-back mode on. This tells the Raspberry Pi to instantly confirm a file is saved the exact millisecond it hits the NVMe. Number 2, the dirty data threshold. We crank this to 40%. This tells the system to aggressively hoard data in the ultra-fast cache until it's 40% full before it even thinks about dumping it to the hard drive. Number 3, sequential underscore cutoff. Normally, Bcache tries to be smart and sends massive sequential files straight to the hard drive. But we only have one hard drive, so we are turning this logic off. Everything goes through the NVMe fast lane. Number 4, We crank the write-back_delay. This forces the Raspberry Pi to wait longer before flushing data, giving our mechanical drive more time to sleep. Our god-tier Raspberry Pi Home NAS array is officially built. We format it to standard ext4 and mount it right back to /mnt/USB disk, which is already mapped in our Samba config. We start the Samba service back up, jump over to Windows Explorer, and create a quick test file. Boom. It pops up instantly. Permissions are locked in, the mount is perfect, and our Chimera drive is alive. Are you guys ready for the final boss? It is time for the ultimate stress test. Let's see what this beast can really do. Alright, the moment of truth. Back in the Windows console, I am firing off the exact same brutal disk SPD test that choked our mechanical drive to death earlier. Hit enter and let's go. While that's hammering the network, let's switch back over to our Raspberry Pi and look at glances. Oh man, look at these numbers. This is beautiful. Our network utilization just shot up to 200, even 300 megabits per second. That nasty eye weight that was freezing our CPU, it has dropped massively. But look right here, this is the real magic. Look at the disk traffic. Our tiny NVMe drive is up there, absolutely tanking the hits, chewing through 30 megabytes a second of pure, chaotic, random I/O. But look at our old mechanical drive, /dev/SDA. It is practically sleeping. It's only sipping maybe 2 to 3 megabytes a second. The load has dropped by an entire order of magnitude. Because this stress test is just spraying random data everywhere, Bcache is working like an absolute boss. It is using our Raspberry Pi's RAM and the NVMe to absorb all the chaos, and it's only trickling data down to the mechanical drive in perfectly optimized sequential chunks when the drive is actually free. And the test is done. Drum roll, please. Let's look at the final disk SPD stats. Boom! Average read and write speeds are sitting at 5 megabytes per second. Do you guys remember the raw mechanical drive test? We were suffocating at 400 kilobytes per second. We just unlocked a massive, greater than 10 times performance multiplier on the hardest possible Home NAS storage workload. But wait, what about normal everyday use? Let's do one final real-world test. I'm grabbing a massive 5 gigabyte media file and dragging it straight to our new hybrid share via Windows Explorer. Look at that transfer graph. It instantly pegs at 100 megabytes per second and just flat lines there. We are completely maxing out our gigabit network on a single sequential write. Zero stutter, zero lag. Our Raspberry Pi isn't even breaking a sweat. We actually did it, guys. We hacked the system. We took a Raspberry Pi, a cheap NVMe, and an ancient hard drive and built a data center level tier storage Home NAS for absolute pennies. If you want to build this exact Raspberry Pi Home NAS setup, the full copy-paste runbook is pinned in the comments below. And if you want to see more about this beautiful Pyramid 5 case with a built-in NVMe slot, click the review video popping up on your screen right now. Smash that like button, subscribe for more insane tech builds, and I will catch you guys in the next one. Peace.